First question is Zener diode is used for, and options are amplification, option B is rectification, option C is stabilization, and option D is producing oscillation in an oscillator circuit. We have discussed that Zener diode is used as a voltage regulator, so it is used to stabilize the output voltage. Therefore, option C is the correct option. While in case of amplification and oscillator, transistors are used, and in rectification, junction diodes are used. Second problem is a Zener diode having reverse breakdown voltage equal to 15 volt is used in a voltage regulator circuit as shown in the figure. The current through the diode is, options are 10 milliampere, option B is 15 milliampere, option C is 25 milliampere, and option D is 5 milliampere. The given circuit is voltage regulator circuit in which Zener diode is under the breakdown reverse bias mode. So voltage across the Zener diode is constant, which is equal to 15 volt, and because 1 kilo ohm is in parallel with the Zener diode, so voltage across the 1 kilo ohm is also 15 volt. Here it is given that this 20 volt is the source voltage and this 250 ohm is the source resistance, and the current through the source is suppose Is. This source current when reach at junction A, it breaks in two components. One is through the 1 kilo ohm, which is the load resistance RL. So this current suppose IL, and current through the Zener diode is IZ. Using the Kirchhoff's current law that incoming current should equal to outgoing current at a junction point. So at junction A, incoming current is IS, it will be equal to IL plus IZ. Here voltage across the Zener diode is 15 volt and it is fixed if Zener is under reverse breakdown condition, and 1 kilo ohm resistance is in parallel with Zener diode. So voltage across the load resistance will also equal to 15 volt. Therefore, the load current will be equal to voltage across load resistance divided by the value of load resistance. It will be equal to 15 volt divided by 1 kilo ohm, that is equal to 15 volt divided by 10 raised to the power 3 ohm. We can write it as 15 into 10 to the power minus 3 ampere, or simply it is 15 milliampere. Now we have to find the source current. The source current is flowing through the 250 ohm, which is the source resistance. So current Is will be equal to the voltage across the 250 ohm divided by the source resistance Rs, which is equal to 250 ohm. So we can write it is voltage across 250 ohm divided by the 250 ohm. Now voltage across the 250 ohm is equal to, because applied voltage is 220 volt and voltage across the Zener diode is 15 volt. So remaining voltage appearing across the 250 and it is divided by the 250 ohm. So it will be equal to 5 volt by 250, or we can write it is ohm. So it is 5 by 250 ampere. In milliampere we can write it is 5 by 250 into 1000 milliampere. On solving it will be 4, so it is 20 milliampere. Therefore Zener current will be equal to Is minus IL, that will be equal to 20 minus 15, that is equal to 5 milliampere. So option D is the correct option. Third question is, figure shows a DC voltage regulator circuit with a Zener diode of breakdown voltage 6 volt. If the unregulated input voltage varies between the 10 volt to 16 volt, then what is the maximum Zener current? Options are 2.5 milliampere, 1.5 milliampere, 7.5 milliampere, and option D is 3.5 milliampere. In the shown circuit, A and B are the input terminals across which a source voltage is applied, and this source voltage has the value from 10 volt to 16 volt. From A source current Is is flowing through the source resistance Rs, and at junction point C, this current divides in two parts. One is the Zener current which passes through the Zener diode, and another is the IL, this is the load current which passes through the load resistance RL, and this RL is in parallel with the Zener diode. And then at junction point D, these two current meets and same source current flow through the input terminal B of the source. Because Zener diode has a fixed voltage which is 6 volt, VZ is 6 volt, and RL is in parallel with Zener diode. So voltage across RL will also be fixed and it will be equal to 6 volt. Therefore, load current will be equal to VZ by RL, and this will be equal to 6 volt divided by 4 kilo ohm, and this will be equal to 6 by 4 milliampere, because volt by kilo ohm will be equal to milliampere, and that is 1.5 milliampere. So load current is 1.5 milliampere. Now we have to find the source current, because source current will decide how much current is to pass through the Zener diode. So source current IS will be equal to the voltage across the source resistance RS divided by the RS. To find the voltage across the source resistance, this B is grounded, so D is at 0 volt, and voltage across the Zener diode is fixed, which is 6 volt, so terminal C will be at the 6 volt, and the voltage at A will range from 10 volt to 16 volt. Therefore, voltage across the source resistance will be from 10 minus 6 to 16 minus 6. That means source current will be 10 minus 6 volt. This is the potential difference between the A and C divided by the source resistance, which is 2 kilo ohm, and it will be equal to 4 by 2, that is equal to 2 milliampere. This is the current when the source voltage is 10 volt, and if source voltage is 16 volt, then the difference between the potential across the RS will be 16 minus 6 by 2 kilo, that is equal to 10 by 2, or it is equal to 5 milliampere. Hence, we can calculate the Zener current, that is equal to IS minus IL, because from Kirchhoff's current law, at a junction, incoming current must equal to the outgoing current, that is 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 the incoming current at junction C, so it should equal to IZ plus IL. So IZ will be equal to IS minus IL, and it will be equal to, if IS is 2 milliampere and IZ is, this IL is 1.5, so it will give 0.5 milliampere. Or in case when the voltage is 16 volt at the point A, then in that case the Zener current will be equal to IS minus IL, and source current will be equal to 5 milliampere as calculated above minus 1.5, it will be equal to 3.5 milliampere. Hence 3.5 milliampere is the maximum Zener current, so option D is the correct answer. Fourth question is, the figure represents a voltage regulator circuit using Zener diode. The breakdown voltage of the Zener diode is 6 volt and the load resistance RL is 4 kilo ohm. The series resistance of the circuit is Ri, which is 1 kilo ohm. If the battery voltage VB varies from 8 volt to 16 volt, what are the maximum and minimum current through the Zener diode? It is just similar to the question number 3. Given that this load resistance is 4 kilo ohm and input resistance is 1 kilo ohm, this battery voltage varies from 8 volt to 16 volt, and the Zener diode, this is a constant voltage under the breakdown state of the Zener diode, is given 6 volt. So we have to find the minimum and maximum value of the current through the Zener diode. This VB gives the source current IS, which at junction A divides in two currents. One is the load current, this is IL, and another is the Zener current IZ. And at junction point B, they again reach and constitute the IS and reach the battery, completing the circuit. So using the Kirchhoff's current law, We know that incoming current, which is the source current at junction A, must equal to the outgoing current, that is IL plus IZ. First we calculate the IL, load current. IL will be equal to voltage across the load resistor divided by the load resistor. Because load resistor is in parallel with the Zener diode and voltage across the Zener diode is fixed, which is 6 volt. So same voltage appears across the load resistor, so it is 6 volt divided by, and value of the load resistance is 4 kilo ohm, so it is 4 kilo ohm. That is equal to 6 by 4, and volt by kilo ohm it will be milliampere. Hence load current will be 1.5 milliampere. It will be a fixed current. Now we have to find the source current. This source current will be equal to the voltage across the input resistance divided by the value of input resistance. This input resistance will be the difference of the voltage at the positive terminal of the battery and at the point A. Considering the B at a ground state, it is 0 volt, and voltage across the Zener diode is 6 volt, so point A is at 6 volt. And this battery have the voltage from 8 volt to 16 volt, so positive terminal value have the range from 8 volt to 6 volt. So according to this, source current will be equal to 8 minus 6. This is 6 is the voltage at the point A, divided by the load resistance, that is 1 kilo ohm, and this is in volt. So it will be equal to 8 minus 6, that is 2 by 1 milliampere. It is 2 milliampere. This is the value of the source current when VB equal to 8 volt. Similarly, source current will be equal to 16 minus 6. 16 is the value of the battery. This is the maximum value of the battery, minus the 6. This is the voltage across at the point A, which is fixed, divided by 1 kilo ohm. So it will be equal to 10 by 1 milliampere, and it is equal to 10 milliampere. This value when VB equal to 16 volt. So Zener current will be equal to IS minus IL. It will be equal to IS is 2 milliampere and IL is 1.5 milliampere, and it will be equal to 0.5 milliampere, and this will happen when VB is 8 volt. Similarly, it will be equal to 10 milliampere minus 1.5 milliampere. It will be 8.5 milliampere when VB, that is the voltage of battery, is 16 volt. Hence minimum value of the Zener current is 0.5 milliampere. This is the minimum, and maximum value of the Zener current is 8.5 milliampere. Hence option C is the correct option. Fifth question is, in the given circuit, the current through the Zener diode is close to, options are 6.0 milliampere, 6.7 milliampere, 0 and 4.0 milliampere. The circuit is the voltage regulator circuit, in which Zener diode acts as a voltage regulator because under the reverse breakdown condition, the voltage across the Zener diode remains constant. Here, this 12 volt is the source voltage, and R1 is the source resistance, which is having the value 500 ohm, and it is connected with the Zener diode, and Zener diode is connected with two parallel resistors R2 having the values 1500 ohm. If we redraw this figure, we will have, this is the resistor R1, which is having the 500 ohm. This is the battery source voltage of 12 volt, and here is a resistor. This is say R2 dash, and this is connected in parallel with the Zener diode, which have the voltage, reverse breakdown voltage is 10 volt. This R2 dash is the equivalent resistance of R2 parallel with R2, and R2s are 1500, so 1500 into 1500 by 1500 plus 1500, it will be equal to 1500 into 1500 by 3000. On cancelling it is 2, and on cancelling we will have simply 750. So R2 dash is 750 ohm. Therefore this R2 dash is 750 ohm. Now if Is is the current flowing through the source, then it will flow through R1, and at junction point A it divides in two parts. One is IR2 dash and another is IZ. So using the KCL at junction point A, that incoming current, which is Is, must equal to outgoing current, and this is Iz plus I2 IR2 dash. Now we calculate the value of Is and Iz. First we have to calculate IR2 dash, that is the current through the resistor R2 dash. It will be equal to voltage across it will be same as across the Zener diode, because this is in parallel with Zener diode. So it is 10 volt divided by, and resistance value is 750 ohm, and it will be equal to 10 by 750 into 1000 milliampere. On cancelling it will be 3, it will be 4, that is equal to 40 by 3 or 13.3 milliampere. Similarly, we can calculate the current through resistor R1, that is equal to source current. It will be equal to voltage across the R1, because voltage at point B, which is at ground, is 0 volt, and voltage across the Zener diode is 10 volt. So A will be at the 10 volt voltage, and the upper terminal of the positive plate will be at 12 volt. So voltage difference across the resistor R1 will be equal to 12 minus 10, and resistor is having the value 500. So it will be 2 by 500 ampere, or we can say it is 2 by 500 into 1000 milliampere. So it will be, on cancelling it will be 2, so it is 4 milliampere. That means if we replace the value here, this will be Is, that is source current, is 4 milliampere. This will be equal to Iz, and the current through the R2 dash will be equal to 13.3 milliampere. So Iz will be equal to 4 milliampere minus 13.3 milliampere, and this is a negative value. Because Iz is negative value, so it is not in reverse mode. So there is a very small current maybe flow through the Zener diode. Hence, we can say that option C is the correct option.